is a period domain of polarized Hodge structures. Basically, it remembers the bilinear form defined on cohomology and also the positions of this HPQ, this Hodge decomposition. And this gamma comes from the local system of this cohomology form to X. If we vary X, and if we go around the modular space S and come back, then we may have some monodromy action on the cohomology of X. So we will have a well-defined period map from the base to the period domain modulo gamma. And global totality theorem says that P is injective. So if in some cases we may have global totality theorem. So when we say satisfies global totality, it means this map P is injective. And infinitesimal totality means we can usually this is easier. So we can just look at differential of this map and try to see whether it's infinitesimally, whether it's injective or not. So we will see some examples. So these are some important famous examples. The first one is a curve of genus greater or equal than 1. So the corresponding period domain is a single up-half space. So basically you consider the H1 of the curve and the Hodge structure there. So I forgot to mention that actually you also need to consider the integral structure on cohomology, and then you will have the corresponding object is called Jacobian of the curve, and the modular space of the Jacobian, or you view Jacobian as a polarized abelian variety, and the moduli is just a single up-half space. And for polarized abelian varieties, you also consider H1, and this is almost tautology. So the moduli, or how this abelian variety varies, is entirely captured by its first cohomology. So this gives you also the single half space. And for polarized K3 surfaces, the corresponding period domain is special is a type 4 domain in Cartan's classification. And we also have some other examples with type 4 domains. The next one is cubic fourfolds. So you consider a cubic equation defined in P5, then you will have some final variety called cubic fourfolds. And it turns out the middle cohomology also has a Hodge structure giving you type 4 domain. And this is closely related to K3 surfaces, or more generally, hypercalar manifolds. So you can consider the functional scheme of lines of a cubic fourfold. Cubic fourfold is a final variety, and you consider the variety parametrizing all the lines on this cubic fourfold, you will find it's actually a hypercalar manifold of dimension 4. And the deformation type of this hypercalar manifold is a symmetric product of two K3 surfaces. And you will have the corresponding type 4 domain. And finally, the example is moduli of points on P1 with suitable weights. So this is a very classical theory. Later I will go into details of this theory. Basically, it's just a period integral of differential form with prime variables. And you consider this moduli and the corresponding period domain. You also have some period map, and it will give you a complex hyperbolic ball. So in all these cases, the period domain is a locally symmetric space, so or Hermitian symmetric space. So in general, for a general variety, the period domain is not very nice. It's not a Hermitian symmetric space. You don't have very good theory studying those things. But for these examples, the pure domain is very nice. It's locally symmetric space, and if you quotient out by this gamma, then you will form a quasi-projective variety, and you have very nice multiplication theory for this quasi-projective varieties. And also those computations have some moduli interpretations. All right, so for the later 5 cases, the paired map will give you a algebraic open embedding. So the domain will form so the moduli is a quasi-projective varieties, sometimes with commutations, moduli commutations, and on the right hand side, you also have quasi-projective varieties. So you can talk about whether it's algebraic open embedding. So in fact, these things are true, and for all these examples, in some sense, the global triad holds. So for polarized hypersurface manifolds, you need to be a little bit more careful. You may have multiple components. All right. So let me say a little bit more about type 4 domain and complex hyperbolic balls. So for type 4 domain, it's defined as follows. We consider a real vector space with a symmetric bilinear form psi of signature 2m. And type 4 domain is a domain parameterizing the vectors, the complex vectors V in this complexification of, this should be W, sorry for the typo. And it's isotropic, so psi VV is equal to 0, and psi VV bar is greater than 0. So you can also interpret this as, so if you take the real part and imaginary part of V, then it will generate a 2-dimensional subspace inside W, and this 2-dimensional subspace will have some positivity properties. For example, this bilinear form restricts to this 2-dimensional subspace should be positive definite. And from this point of view, this type 4 domain is also a subset of Grassmannian. Alright, so that's one symmetric domain, and the other one is called a complex hyperbolic ball. Now we consider a complex vector space with Hermitian form of signature 1m, and the associated complex hyperbolic ball is just a set of all the positive lines inside this vector space. So these are two important symmetric domains. And next, we will consider some constructions called a cyclic cover. So if we have a variety V, and we consider a D21 cover branch along just one divisor X, and this covering admits a deck transformation, which is this cyclic group. So a very beautiful example, well-studied example, is taking V to be P3, and we take degree 3 hypersurfaces, they are cubic surfaces. So it's a final surface is a dipedal surface, and Y is a cubic threefold. So if you take the 3 to 1 covering over this, you will have some very special cubic threefolds. And cubic threefold is also a final variety, and you consider the middle dimensional cohomology, then this group, this cyclic group will act on it, and you will have this decomposition, eigenspace decomposition according to these characters of the cyclic group. So in this case, it decomposes into 2 parts. Let's see what's the detailed structure of this, or Hodge structure for this decomposition. So for a cubic threefold, the middle dimensional cohomology has is 10-dimensional, and the Hodge numbers are 0, 5, 5, 0. And if we use this cyclic group, consider this cubic threefolds with this special symmetry, then the decomposition of cohomology or Hodge numbers will be 0, 1, 4, 0 and 0, 4, 1, 0. And if you look at, if you look at, for example, H3 chi y, then the bilinear form on the middle dimensional cohomology by Poincare duality will induce a Hermitian form. So in this case, actually it's a skew Hermitian, but you need to multiply it by a pure imaginary number to make it a Hermitian. Then this Hermitian form will have signature 1, 4. And the Hodge decomposition or Hodge structure in this case, you just need to take out the position or where this H21 is. So you consider one-dimensional subspace inside a 5-dimensional space together with a Hermitian form of signature 1, 4. And this H21 is positive definite under this Hermitian form. So the period domain is exactly a 4-dimensional complex hyperbolic ball. So a famous work by Alco, Carlson, and Toledo gives you global toriality for this case. So you consider M to be the moduli of stable cubic surfaces. So here, in the previous case, when V and X are smooth, then Y is also smooth, so you consider smooth cubic threefolds. But when it's not smooth, you also need to capture the degenerations of those varieties together with degeneration of Hodge structures. And it turns out, in this case, everything is very nice. So you can have a GIT moduli of all these cubic surfaces, and the corresponding period domain is 4-dimensional hyperbolic ball quotient by a arithmetic lattice acting on B4, and the you have a very natural commutative called Bailey-Borel commutative. This is also how people prove that the original variety is quasi-projective. And in fact, you only need to add some points at infinity to this B4 modulo gamma. But if you fill in all these singular cubic surfaces, suitable singular cubic surfaces, and on the right-hand side you fill in some points, then this paired map is bijective. So
this is this H3 chi y, that fixed point or something like that?
So it's the eigenspace decomposition. So you consider the cyclic group action, and you will have two characters, and it's a decomposition of this type. All right. Any questions? All right, so let's continue. So for this example, you really need to first add some cubic surfaces with mild singularity. So for this period map, it's not even surjective. So if you only consider smooth cubic surfaces, it's not surjective for the interior of the ball. So you need to fill in some cubic surfaces with mild singularity, which will give you the interior, fill in the interior of this ball. And you also need some cubic surfaces with really bad singularities. And those things will correspond to the boundary or the boundary points on the ball quotient on the right-hand side. So you add two different types of cubic surfaces. All right, so in the previous case, it's a cyclic cover over P3. So we can also study cyclic cover, for example, for P1 cross P1. So this is Kondo's example. So Kondo considers a modular space of curves of genus 4. So from well-known theory about low genus curves, we see that if you consider canonical embedding of genus 4 curve, it will be mapped to P3. And inside P3, generically, it's always, so if it's not hyperelliptic or theta invariant not equal to 0, then it's an intersection of smooth cubic and smooth quadric. And this smooth quadric inside P3 will be isomorphic to P1 cross P1. And so when you take the intersection with the cubic, then the by degree will be 3, 3. So we consider the canonical embedding and consider this quadric, which is P1 cross P1, and take the triple cover branch along this curve of genus 4. Now, the corresponding surface will be a K3 surface. So this is a very nice case studied previously. And the Hodge structure or the cohomology of S will have a similar decomposition according to the character space, according to the character of this cyclic group of order 3. And in this case, we also have a Hermitian form. Now it has signature 1, 9. And what we know is that the moduli of genus 4 curves also has dimension 9. So use this construction, we will have a birational map from moduli space of genus 4 to this Bohr quotient. Now, so this is birational from the previous study of global totality for K3. And if we want to consider compactification on both sides, then it's a little bit more complicated than the previous case. So for genus 4 curve, the very famous compactification is Deligne-Mostow compactification of stable curves. So you add some curves with nodal singularities. And on the right-hand side, you have Bailey-Barrera compactification, for example, is canonical. But when you add those nodal curves, is no longer well-defined. So you no longer have a well-defined period map, and it's not surjective. So in fact, Konda also studied the birational geometry behind, for these two sides. You need to blow up something and blow down something, and this is also explicit with a modular interpretation. So in this case, we also have some similar theorem like global totality, but it's a little bit more complicated. So this Bohr quotient, this 9-dimensional Bohr quotient we will see later, is also the unique 9-dimensional Deligne-Mostow Bohr quotient. So Deligne and Mostow studied a lot for Bohr quotients, and this is a top dimensional example in their list. So this is the same up to a finite cover. So if we consider a low genus example, for example, if we consider curves of genus 3, then by canonical embedding, it will be a quartic curve, degree 4 curve in P2. We can consider degree 4 cyclic cover of P2 branch along D. This is also a K3 surface. And we can consider also this birational geometry. Now, moduli has dimension 6, so you can imagine actually the corresponding Bohr quotient also has dimension 6. So you get also a birational map to a 6-dimensional Bohr quotient in a similar way. Alright, so that's Kondo's work for cyclic cover, basically branch along surfaces. So P1 cross P1 or P2. So any questions for this part? Alright, let's continue. So we can also do some cyclic cover for higher dimensional case. So if we take the base to be, let me see, this base is P4, and the branching divisor is a cubic threefold. So we consider the modular space of cubic threefold. This is a 10-dimensional modular space. And we consider also degree 3 cyclic cover branch along this cubic threefold. And this will give us also a final variety is a cubic fourfold with this degree 3 cyclic group action. And we consider the cyclic group action and the decomposition, so we will have character chi part, character chi bar part, also the invariant part. It's just from, so H2 of P4 is equal to 1, dimension equal to 1. So we have 1, 10, 10, 1, and 1 here. And this is again the work by Elko, Carson, and Toledo, also by Luyanha, Swearstra, simultaneously at around the same time, independently around the same time. So you consider the moduli space of cubic threefold, and on the right hand side, you don't have Bailey-Borel quantification. It's another quantification called Luyanha's semi-toroidal quantification. So let me explain a little bit more. So in this quantification, so when you consider the moduli space of all the smooth cubic fourfolds and consider the period map, it's not surjective. So you will miss some hyperplanes. So when you consider type 4 domain or hyperbolic balls, it's like what you did for real hyperbolic geometry. You have some very special total geodesic subvarieties. So in this case, it's totally geodesic divisors or Huygens divisors inside this ball or type 4 domain. And if you consider the original period map, it will miss some hyperplanes or miss some divisors. So those divisors will have two different types. One is something you can fill in when you consider cubic threefolds with mild singularity, or in this case, ADE singularity. So if you consider those cubic threefolds, you can fill in those locus, some locus or some Huygens divisors or some hyperplane arrangements inside B10. But for some other divisors, it's not filled in by smooth cubic fourfolds. You need to consider, not by some cubic fourfolds with ADE singularity. You need to consider some cubic threefolds with very bad singularities. And those cubic threefolds with bad singularity in GIT theory is also bad. They're not strictly stable points. They will correspond to semi-stable points. And the modular space will have bad singularities along those locus. And on the right-hand side, you also miss some some other hyperplane arrangements. So you need to. So if you consider the dimension on both sides, so the dimension of the source and the dimension of target are not the same. So the hyperplane arrangement will have a higher dimension. So in this case, you first need to blow up the Bailey-Borel quantification. Is called semi-toroidal. So it's analog of toroidal quantification. So you need to blow up the boundary points and then also contract some divisors along some directions according to this hyperplane arrangement. So you have some birational operation which has a Hodge theory interpretation on the right-hand side. And if you do this operation, this birational operation, then you have isomorphism from left to right. So the right-hand side, I will call it Luyanha's quantification of ball quotients. So it's a ball quotient associated to some hyperplane arrangements. And especially when this H is empty, so the semi-toroidal quantification is just Bailey-Borel quantification in this case. And also, this quantification, for example, the Bailey-Borel quantification has a very nice interpretation in terms of modular forms. So if you consider the ring of modular forms, you take the approach, then you will get a projective variety which is Bailey-Borel quantification. That's also how people prove that Bailey-Borel quantification is projective. And in this case, you also consider modular forms, but these modular forms can have or allow some poles along those divisors, along those hidden divisors. So on the right hand side, it's also a ring given by the approach of a ring of modular forms with potential poles. All right, so that's another famous example, and in this example, we no longer have Bailey-Borel kind of commodification. Also, this work is quite influential because later people like Lada, they proved the surjectivity of global surjectivity of period map for cubic fourfolds, and it also borrows some ideal and analysis from this work. Right. So let me say a little bit more about my joint work with Zhiwei Zheng in this case. So we consider also cubic fourfold, recall that. So in the previous case, this is actually a cubic fourfold with cyclic group action of order 3. We consider any group action. So if you consider any finite group action on cubic fourfold, then we can consider the modular space of those cubic fourfolds with this type of symmetry. So you will have cyclic groups or some other abelian groups or even non-abelian groups. So there are many examples of those groups. And the corresponding cohomology will have a decomposition according to the character or according to the representation of finite groups. And we can have also a type 4 domain or a complex hyperbolic ball as its period map. So this type depends on the image of G inside or the G action on the H31 part of the cubic fourfold. And we will have a arithmetic group acting on the cubic, acting on the type 4 domain or the complex hyperbolic ball, and also a hyperplane arrangement inside this period domain. And we prove that the corresponding period map in this case also gives you a isomorphism from GIT moduli to the Loyang compactification on the right hand side. So the case of cubic surfaces and cubic threefold can be interpreted as a special case for this theorem. So, for example, in the previous case, this is a this moduli of cubic threefold is just a cubic fourfold with cyclic group symmetry, and if you consider, for example, cubic surface, you can. So in this case, if you have an equation of a cubic surface, then you can add y1 cube, y2 cube to this equation. This is a cubic fourfold with symmetry. This symmetry will be cyclic group, product of cyclic group. And in this case, we can also have a similar story using the Hodge structure of cubic fourfolds instead of Hodge structure of cubic threefold in this case. And it will give us a similar result as before. And we also have some criterion when the right hand side is actually a Bailey-Borel compactification.
Complex computation, we'll get some result over R.
So we consider the group action preserving the complex structure. So it's just the automorphism group, the finite subgroup of the automorphism group of the cubic fourfold. So let me say a little bit more about the key ingredients in the proof. So the key ingredients first is from the work of Zhiwei Zheng, Loyang and Laza. So first, Zhiwei proved the global toriality for cubic fourfolds earlier, when I think in 90s or 80s, I forgot. So later, Laza proved the surjectivity of the period map, and also they found a gap in the original proof for global toriality in Zhiwei, and Zhiwei, Loyang, and Laza also fill in those gaps after Laza's work. All right, so this is global toriality for all these cubic fourfolds, and Laza has a very detailed characterization of the image of period map, and using Loyang's work for computification of this type 4 domain quotient, then they have some results in this form for all the moduli space of all cubic fourfolds. And if we consider the moduli of cubic fourfolds with spatial symmetry, now on the GIT side, actually the group, the reductive group, is a little bit smaller. So in this case, for example, let's look at the previous example for cubic threefolds. So if you consider all the cubic fourfolds, then the GIT action is actually a general linear group of dimension 6, and for cubic threefolds is a general linear group of dimension 5. So the reductive group need to preserve the group action. So in this case, actually the moduli space, the GIT moduli space from this cubic fourfolds is a little bit different from the locus you see in M. So it's actually the normalization of its image, and it's finite. So we need some study, a GIT study on the left-hand side, but this is essentially the theorem by Lunar. And on the right-hand side, we have the corresponding period domain and the corresponding map on period domains. So in this case, we need some functorial property for computifications of, or semi-toroidal computifications for type 4 domains, or bulk quotients to type 4 domain. So on the right-hand side, so for the usual Bailey-Borel computification, we have this functorial properties, maybe essentially back to Bailey and Borel, and later Harris proved the functoriality of toroidal computifications. And in this case, for semi-toroidal case, we also prove the functoriality on the right-hand side. So if you have the functoriality on both sides and you have very nice correspondence on the bottom row, then you prove upstairs they are also very nice. All right, so that's a key ingredients for the proof. We borrow the existing results and prove the functorial properties for those maps between moduli and pure domains. All right, so that's the proof for this case. So let me say a little bit more about the classification of automorphism groups. So this is mainly the work of my collaborator Zhiwei Zheng. So he and Laza classified or gives all these 34 finite groups, which can be the symplectic automorphism group of cubic fourfolds. So for symplectic, it means the action on H31 is identity. So in this case, all these period domain are type 4 domains. And later, Yang, Yu, and Zhu, so, they proved that, or they classified all the finite group that possibly can act faithfully on cubic fourfolds. So if in this case the action, if it's not symplectic or it's not real, then it will give you Born quotients. So from this classification, you can read out a lot of type 4 domains and Born quotients. They all have the modular interpretation as cubic fourfolds with some special symmetry. All right, so any question for this part? If no question, let's, yeah. This is a stronger form for the global totality, right? So global totality means for the smooth part, this is the injective map from left to right. And here we also prove kind of surjectivity on the right-hand side. So essentially, something is not surjective, you need to include singular objects to fill in those locus, and this bidirectional transformation will tell you which locus you need to fill in to which mild singularity you need to include, and which bad singularity you also need to include, but on those locus you may not have surjectivity, so on the right hand side you need to contract some divisors to get isomorphism on both sides. So it's in some sense it's a stronger form of global totality. Yeah, including the boundary. Yeah. Not just the boundary, because if you want surjectivity, you also need to include some cubic fourfolds with mild singularity. They are not smooth.
What kind of curves correspond to left-hand side?
So yeah, so a very good question. So on the right-hand side, for example, there is some famous construction of cubic fourfolds called determinantal cubic fourfold. It's just given by determinants of matrices of very symmetric 3x3 matrices like A, B, C, C, E, F. Something like this, and then if you take determinant, it will give you a very singular but with high symmetry cubic fourfolds. And actually, for many cubics, higher dimensions, you also have this kind of examples. Any other questions? So if no question, let's consider a lower dimensional example. So it's dimension 1. So you consider a cyclic cover of P1 branch along points, along, for example, n plus 3 points. And then you have a degree D cyclic cover. And here, different from the previous case, we can allow some multiplicity at those points. So we put some power of AI here, and I require this number, this rational number is from 0 to 1 for convenience. If it's not, then you can make it to be in this range just by dividing some factors. And in this case, the cyclic group will act on it, and you have the characteristic decompositions. And if we look at, essentially we only need to look at the tautological character, or the other cases are also induced by this case. And if the summation of the weights is equal to 2, then this tautological character space will have Hermitian form of signature 1n. And if you consider modular space, it will also have dimension n, because this PSL 2C have dimension 3, and n plus 3 minus 3 is also n. And you also consider the monodromy representation from pi1 m to pu1m. And in this case, it's a little bit different. So when you consider the Hodge structures, if you consider integral Hodge structures, the monodromy representation is always discrete. But for now, you consider some factors of the monodromy representation, and you consider some factors of the original Hodge structure. And for example, in this case, you need to enlarge your field, so you don't consider all the integral Hodge structures. You need to consider Hodge structure defined on some number fields. then it's no longer discrete. So it's not automatically discrete. So in many cases, actually, this monodimensionalization will give you a non-discrete action on the hyperbolic ball on the period domain. And Deligne-Mostow, so also some very important previous works by Ola, Riemann, Schwarz for n equal to 1 or one-dimensional moduli space case, and Picard for two-dimensional case, and many other people generalize this. And finally, Deligne-Mostow proves that this is also gives you a global toriality or isomorphism from moduli space of those points. So those weights will give you a GIT commutative, and on the right hand side you consider the Bailey-Borel commutative if gamma satisfies some Schwarz type condition. So Schwarz first come up with this condition for dimension 1 case, and for higher dimensions there Picard also gives you some conditions for dimension 2, and finally Deligne-Mostow give you the conditions for all dimensions, and if it satisfies those conditions, then this will give you isomorphism. And in this case, actually, there are only 94 examples, only very many examples satisfying this Schwarz type condition when n is greater or equal than 2. And when n is equal to 1 is essentially already started by Schwarz. All right, so why this Ball quotient is important? So first, they find these 94 examples satisfies the Schwarz condition, and also later, Mostow find 10 more examples. They form all the discrete examples for n greater or equal than 2. So there is the largest one with n equal to 9. That's the previous Ball quotient we mentioned from Kondo's example of genus 4 curve. And important thing is the arithmeticity. So from these 104 examples, there are some non-arithmetic lattices in PU12 and PU13. So in PU13 there is only 1, and for PU12 there are around 10. I don't remember the exact number, but around 10. But there are some also other constructions of non-arithmetic lattices in PU12 and PU13, continuing the work of Mostow, and it remains still open to find more non-arithmetic lattices in acting on this complex hyperbolic Ball quotients. So we don't know whether there exist non-arithmetic lattices for acting on complex hyperbolic ball of dimension greater or equal than 4, or we don't know whether there are infinite many non-arithmetic lattices for each dimension n. So this is still open, and this is the last open case for simple groups. So for all other simple groups, we either know some rigidity theorem, which says that there are only arithmetic lattices by Margulis superrigidity, and also 2 other cases by Gromov, Shen, and Colette. And in the remaining 2 cases, actually, so PU1n or O1n, so corresponds to complex hyperbolic geometry or real hyperbolic geometry. And for real hyperbolic geometry, Gromov, Pierre-Teskey, and Shapiro already give you infinite many classes of non-arithmetic lattices. So here, commutability means they are different by up to a finite cover. So if they differ by finite cover, they're both arithmetic at the same time. So we need to classify them up to commutability classes. So they find infinite many for a fixed n. And for complex hyperbolic ball, it's still widely open. So for now, people only have around like 20 examples of those non-arithmetic lattices. All right, so that's finishes the story for cyclic covers or varieties with symmetries. Next, let's discuss some constructions by degenerations. So we also want to construct some examples with global triadic hosts, a stronger form of global triadic host, we want some isomorphism from modular space to this quantification of Hermitian symmetric spaces. And this example is given by Shar. So generically, if we consider the most simple polarized case-free surfaces, so we have a very simple, the most simple polarization is just a degree 2 ample divisor. Then if we consider the linear system corresponds to this degree 2 divisor, then the linear system will have dimension 2. So you will have a canonical map from case-free surface to P2, and it will be a double cover. Generically, it will be a double cover branch along a smooth sextive curve, a curve of degree 6, which has genus 10. And Shar proved that, he first proved that this also gives you a commutafication from modular space of sexy curves to some commutations of this type 4 domain. And later, Luo-Yang generalized the birational construction of Shar to construct this Luo-Yang commutafication. So by the machinery, so Luo-Yang's work is comes later than Shar's, and using Luo-Yang's the machinery, you can also prove that there's a explicit birational transformation giving you the isomorphism from modular space of sexy curve to this 19-dimensional modular space of full symmetric variety. Right, so that's a basic case, and we consider degenerations of, or singular, in some sense, singular locus for those moduli spaces. So for example, we can consider sexy curves with nodal singularities. So for example, if we consider a quintic and a line, then they will intersect at, generically intersect at 5 points. So in this case, it's a modular space of sexy curves with 5 nodal singularities. And of course, you can also have a sexy curve with irreducible, just one irreducible component and 5 nodal singularities. There are different topological types. But for each of those topological type, we can have a similar theorem about modular space of those singular sexy curve with Luo-Yang commutafication of a type 4 domain. And for example, in this case, if you consider modular space of quintic and line, then we can have isomorphism from a, we have 5 nodes, so the dimension will be decreased by 5. So it's a 14-dimensional type 4 domain. And the proof is similar. On the GIT side, we need to work a little bit different than the previous case. So we consider the GIT of singular objects. We still have functor reality property on the left-hand side. And on the right-hand side, we also have the functoriality similar as before. So in this case, you consider degenerations of those varieties. And in some sense, the degeneration will give you some automorphism for Hodge structures, and you do a similar theory on the right hand side, you have this isomorphism. Alright, so maybe let me say a little bit more about the relation to Deligne-Mostow surfaces. So we know that a Deligne-Mostow surface of degree D is a blow up of P2 at 9 minus D points with general position. And here, it's also related to sexy curve. We can consider irreducible sexy curves with 9 minus D nodes. Then the resolution of C tilde is smooth curve of D plus 1. And we blow up those nodes, we will get a Deligne-Mostow surface. And the case-free surface we obtain here is a double cover of the Deligne-Mostow surface. So essentially, the previous construction for type 4 domain comes from these double covers or these case-free surfaces. The smooth case-free surfaces. And there are some other works relating the moduli of K3 surfaces, moduli of deposited surfaces also to Ball quotient, not to type 4 domain. So from the previous approach is related to type 4 domain, but we can also have a moduli interpretation in terms of Ball quotients only for these degrees. So degree 1, 2, 3, and 4. They have very different constructions. Some are already known, for example, cubic surfaces. So I won't say details for each construction, but there are also very interesting geometric varieties related to those things. All right. So let me use the rest of the time to discuss cyclic covers. So if you consider cyclic cover of P3, you can consider, for example, in the previous case, you consider cyclic cover branch along a cubic surface. But now you can also consider cyclic cover branch along a hyperplane, along 6 hyperplanes in general position. Then you obtain a Calabi-Yau threefold instead of a final variety. So if the degree of the hypersurface is higher, you do branch covering, you will obtain final Calabi-Yau varieties or general type varieties. So you have a Calabi-Yau manifold, orbifold amidst Krappan resolution. So you will have a Calabi-Yau manifold. And mu3 operation decompose the Hodge structure of H3y as follows. So this is also true for the Krappan resolution. And this is 1, 3, 3, 1. And the corresponding period domain of this Y is a 3-dimensional ball. And this 3-dimensional ball is related to Deligne-Mostow, the example of 6 points. So it says you have the corresponding period map. In other words, you also have an interpretation of this 3-dimensional ball quotients in terms of moduli of Calabi-Yau threefolds. So here are some remarks. Zheng and Xu, they prove the global totality for this family, essentially borrowing the theory of Deligne-Mostow. And Zheng, Xu, and Zuo, they more generally they classified this kind of examples. This is a default covering of Pn branch along n+3 generic hyperplanes, and they are all Calabi-Yau orbifolds with a period domain of n-dimensional, but in most cases, the monodromy group will act discretely or is non-discrete. It will not act discretely on Bn, so it's non-discrete subgroup in this case. All right, so inspired by their work, we consider cyclic covers along P1 cross P1 cross P1. So we consider the degenerations. So we combine the method of cyclic cover and degenerations. So we consider degenerations of these divisors. We consider the degeneration types, different degeneration types. And this will give us also some Calabi-Yau orbifolds, and they all admit Krappan resolutions, which gives us Calabi-Yau manifolds. And those Calabi-Yau manifolds will have different Hodge structures, and we classify the ones with Hodge structures being this complex hyperbolic type. So we classify those examples. So this family will give us complex hyperbolic ball if and only if the divisors have these types of decomposition or their refinements. For example, I can further decompose 3, 2, 0 into 3, 1, 0 and 0, 1, 0. Then it will still be in the list. So we have a complete list, and these are the maximal examples on the refinements. And they have dimension 9, 9, 7, 6. And for the first one is related to Deligne-Mostow, and the second one is also related to Deligne-Mostow, but for the third one, it's not directly related to Deligne-Mostow theory. So in this case, we consider Calabi-Yau orbifolds, the Hodge structure of Calabi-Yau orbifolds, but they form a piece inside the Hodge structure of Calabi-Yau manifolds. So you can say both. Yeah. So if you consider pure domain for Calabi-Yau orbifold or pure domain for Calabi-Yau, the corresponding resolution, they're the same. But if you deform them a little bit in Calabi-Yau manifold, then things will be a little bit different, but we have also some study on this side. But first, maybe let me finish this part. So we have a construction called refinement and half-twist. So for refinements, we just take further decompositions of those divisors or further degenerations. And for half-twist, we're going from dimension 3 to higher. So maybe we can consider products with P1 and then add some divisors and consider the corresponding cyclic cover. And both operations will give us, will start from Borel quotients and give us further Borel quotients. So these refinements or half-twist operation will give us also Borel quotient examples. So when the base is P1 to the nth power, then these two operations will give us also we classify all these examples. So concerning your question, so we can see whether when we do the corresponding resolution, whether the Calabi-Yau manifolds have the same moduli. So in other words, the deformation of the Calabi-Yau manifolds is the same as these orbifolds. So we also have some classification of those results. So they're given by these examples and their refinements. All right. So the approach to the classification, I won't say a lot more on this. So we need infinitesimal tonality and some calculation of Hodge numbers based on Euler characteristics. And there are some combinatorics behind this. And finally, we find the Hodge numbers, and we try to see when this is 0, then this involves combinatorics of this decomposition, and we can see that it will be those examples. So most of these quotients are related to Deligne-Mostow's Borel quotients branch covering over P1 by the following method. So for example, let's take just product of two P1s. So our theory also works in this case. So we consider D1 is a divisor of by degree 3, 1, and the other divisor is a divisor of by degree 0, 2. So this will be this blue curve, blue lines, and green curves. And they will have some discriminant locus when you project to both directions. And in this case, we obtain a case-free surface with double elliptic fibrations, and using Kodaira's theory for elliptic fibrations, we see they are related to Deligne-Mostow's example with those weights. And in this case, we have a byproduct, so we have a commutability results for Deligne-Mostow lattices. In fact, using this similar idea, we obtain the classification of Deligne-Mostow lattices up to commutabilities. So in dimension 3, or these examples, most of the examples are isotrivial fibrations of case-free surfaces, of rigid case-free surfaces. And this also gives us Deligne-Mostow data. All right, so that's all my talk. Thank you again for listening, and thanks for the invitation.
Okay, thanks, Professor Yu. Is there any question?
Yeah. This one?
Maybe later. Yeah, this one.
Yeah.
So you said most of the Borel quotient from P1 and above are comparable to Deligne-Mostow Borel quotient. So how about the remaining of the Borel quotient?
We don't know yet. So at least from the known constructions, the relations methods to relate those Borel quotients to Deligne-Mostow doesn't work for these examples. So in our paper we say this, but maybe let me say a little bit more here. So for example, this third example is not isotrivial fibration of K3 surfaces. So you do have some moduli, or the fibers will vary. So it will not work by the usual construction, the usual methods. So we need to do something more in these cases. Yeah.
The whole has a combinatorial structure here. And is there a relation between the combinatorial structure and the cohomology group?
Yes, so this is in this part. So we need to calculate some Hodge numbers, and corresponds to the decomposition types of those divisors. So so how they decompose, and then how they influence the topological types. So we need those things. And also in high dimensions, we have similar formulas. Yeah. Cohomology ring. So the cohomology ring for cyclic cover is very simple. So it's just from the base, P1 to the nth power, and additional part is in middle dimension. And in middle dimension, we have calculation of those Hodge numbers. I think you know the cohomology structures for this middle dimension case. Then you combine those, you have the cohomology ring for the whole cyclic cover, if you consider the Calabi-Yau orbifolds. But if you do quadrant resolution, you have some contributions by blowups. And essentially, when we prove the completeness of those families, we want to see when this contribution is trivial. But when this contribution is not trivial, for example, in three-dimensional case, you will have some components given by cohomology or Jacobian of curves. So if you add those information, you will have the whole cohomology group structure, cohomology ring structure for this Calabi-Yau manifolds. Yeah.
Any more questions? Okay, if there are no questions, let's thank Professor Chenglong for the next talk.
Thank you.